Are you watching? Okay. So in data, you have like thingies, right? You have thingies. Right? So you have like these like probability values, right? For example, rolling a dice, you would have 1, 2, 3, 4, 5, 6, right? And there would be a uniform distribution, but nobody looks close. So you have these discrete values. This is a discrete function, right? It's not a continuous function, right? So if you wanted to find out the like total, the sum of all the probabilities, which is always just 1, right? So what we do is just add up these values. So with that, you just use the sigma notation as summation, right? But Isaac Newton thought that was dumb. He came along and it's like, what if you have a function like a Java math.random function, right? Like this is what it looks like, right? From 0 to 1. Every number has an equal probability. So if you think about it for a second, right? Let's see, every number has some probability, okay? We'll just call this x, okay? Every number has an equal probability.
I don't know that one. See, I forgot what's happening.
Okay.
Let's go back.
This graph represents the probability of every number from the Java math algorithm. Okay? Okay, well, the thing is, that one has a finite limit. Like, how long is it? 16 digits? Let's say you're truly generating random number, right? So every single number between 0 and 1, how many numbers are between 0 and 1?
Same thing.
Yeah, an infinite number of, there's an infinite amount of numbers between 0 and 1. So any number here, we'll call this probability x, okay? So it has x probability, okay? This means if you add up all the x's, it should equal 1, right? Right? But here's the thing. If you're adding up an infinite number of things, you say x1 plus x2 plus x3. If x equals 0, for example, well then it's just going to be 0, right? So x has to be greater than 0. So if every x value has to be greater than 0. But if you're adding up, let's say 0.1 plus 0.1 plus 1, if you add that off, any number greater than 0, if you just add it to a sum, an infinite number of times, what's it going to be? Infinity, right? If you're just adding any constant number, any number greater than 0, if you add it to itself an infinite number of times, because remember, there's an infinite number of digits between 0 and 1, it's just an infinity. So does that mean that there's an infinite probability? Well, now you find a contradiction, and now you find a problem. And so Isaac Newton thought, alright, time to fix math. This is really funny, right? So what he did was, when you calculate under the, so one thing you notice is that this probability distribution, all the probabilities, it's also equal to the area under this curve, this area. So if you notice that this is the discrete function, right? When you have values like this, it's same as the area under the curve, except there's no curve, it's just the area under the point. So this point, this point, this point. You're just looking at the value between the area under these lines and you're adding them up, which is the summation, right? But here's the area under a continuous function, it's a curve, or like a straight line in this case. If you add up all this area, you get the total probability. And so Newton created something called the integral. This thing. So in C1 tradition, you have like n equals something. So you start out a number and you increase it by increments until you reach a cap, right?
How long would this lesson be?
A long time. With integrals, you can have this notation where you just don't put anything, and this is where you're solving for like the integral as like an equation and not like a finite value. But if you integrate from like two numbers, so let's say 3 to 4, okay? You have here from 3 to 4. You find the area under some curve, so let's say I have this function. From 3 to 4, you find the area under this part. You're trying to find this area of a function. So this is where you get introduced to the fundamental theorem of calculus. So if let's say the function x squared, so this is the notation. So derivative x squared. I need to explain one thing. So how do you go about calculating this area? Let's say 4. Well, what you can do is you can start with a rectangle, okay? So you start with a rectangle, so you approximate. This is really bad realizing, you're approximating the area under the curve. You see how like this gets you like 99% of the area, but not 100% of it, right? So you're pretty close. So then what we do is we call this distance, we call this dx, okay? What we do is we make this dx smaller. It's smaller. And you can see the process is like, it's covering more and more of the area, right? You see that? So if I like continue, right, I'm not going to draw the entire thing. But if the dx is really small, it covers, like you see these gaps are really small and smaller, right? So we want to make dx infinitely small. And so I'm not very well versed in calculus. Or well, in derivatives and limits, I'm pretty decent, but integration is very difficult, so no. But what Newton says is the fundamental theorem of calculus, if you want the fancy words for it, if you take the antiderivative of the integrand, which is this part, it's equal to the area under the, it's equal to the integral from these, if you take like the antiderivative, you plug in these values for it, so the values at its endpoints, and you find the difference.
The antiderivative.
Yes, so the antiderivative, so
The whole of the antiderivative.
if, let's say you have f of x, okay, let's say you have g of x, okay? You have some function called g of x, and we want to find its integral from a to b, okay? Okay, we need first take g of x antiderivative. So let's say f of x, the derivative of f of x is equal to g of x, right? Then g of x antiderivative, which is f of x. Okay? So now we have f of x. So now we do f of x at. So then all we have to do is f of b. So we find f of x at b minus f of a. And that is equal to the integral of this point. You keeping up? Nope, no idea? Right. Well, that's fine. I'll show you with an actual example. Okay? So first we find the antiderivative of x squared.
Antiderivative.
Don't worry about it, don't worry. So it's 2x. I think we put a dx here. I don't know if you put the dx. From 4 to 3 on these intervals, okay? Then all you do is
Are you recording this?
I'm super not. I think I got messed up somewhere.